Welcome to the magnetic force section. So we started off in this course learning about the electric field. An electric field is created by a charged particle or multiple charged particles create an electric field. For a magnetic field, you need moving charged particles. If the charged particles are moving in a wire, we would call that the current. So moving charged particles create a magnetic field. So if the particles aren't moving, we don't have a field, a magnetic field. So we also looked at an electric force. If you have a charged particle in an electric field, it experiences an electric force, and that is given by the equation the electric force is equal to the charge, which is experiencing the force, times the electric field at the location of that charge. Now we are going to look at the magnetic field. For a magnetic, we're going to look at the magnetic force. For the magnetic force, you need a moving charged particle. This could either be a single charge or it could be current moving in a wire. So we're going to have two different equations for the force, one for a single charge and one for current going in a wire. And the book starts off on page 11 looking at the force on single moving charges, but we're going to start off looking at the force exerted on a wire which is carrying current, because that's what our next lab is on. So we're going to come back after looking at the force that's exerted on a current carrying wire. Then we're going to come back and look at the force that is exerted on single charges. Okay, so the moving charged particles can either be moving on their own or moving as a current in the wire, but they do have to be moving. If they are at rest, which would, in the case of a wire, mean the current is zero, then there is no force. But not only do the particles have to be moving, they have to be moving in the correct direction. So if they're moving parallel to the magnetic field, then the force exerted on the particles is zero. So we will have two equations, one for the wire, and that's going to be the magnetic force is equal to I, which is the current, times L, which is the length of the wire, but it's a vector, so the direction of this vector is the direction that the current is going in, crossed with B. I hope you're very excited to see the cross product popping up here. We're going to see it over and over again in the magnetic force section, but luckily for us, taking the cross product in this section will be fairly easy. So usually these vectors are one-dimensional vectors, they might be two-dimensional vectors, and oftentimes you can just figure out the direction of the cross product using your right hand. And if it's a single charge, we will calculate the magnetic force by doing Q, which is the charge of the particle, V, which is the velocity, crossed with B. And those are the two equations which we'll be using most often in this section. If you put this equation for the single charge together with this equation for the electric force on a single charge, you get the Lorentz force law. So this would include both the electric force and the magnetic force acting on a charged particle, moving in an electric field and a magnetic field. Okay, so without further ado, we will move on to our first example problem for the magnetic force.